Hello, welcome to another maintenance lecture. Today we will talk about two topics, the topic of RAM analysis and maintenance strategies. And if you're curious about it, stick until the end because it's going to be a fun and informative ride. Let us start by discussing the relevance of RAM analysis. RAM is a type of analysis that it is used to assess if a given system, such as an aircraft engine, is performing well and if the maintenance is being done efficiently. This framework is in fact not new. It has been extensively discussed both in theory and in practice when we are analyzing complex and critical systems. RAM analysis is frequently used to address maintenance concerns, but also to identify potential failure points of a system. By using RAM analysis, we can gain valuable insights both into the reliability of the system and also about its ability to remain available and operational when needed. This analysis helps us to address maintenance challenges effectively, to enhance system performance, and also to minimize the risk of failure. We have here a graphical representation of RAM analysis in which we show the three dimensions of RAM: reliability, availability, and maintainability. As you can see, the availability is shown in between reliability and maintainability, and this is because it accounts for both dimensions. It is like a summary of the dimensions of reliability and also the dimension of maintainability. Looking at the history of RAM analysis. The concept of RAM is actually not new and has been around for several decades. Its roots can be traced back to the mid-20th century, when the formal development of RAM analysis began during the 40s and the 50s, particularly in the military and due to aerospace applications. During the 40s and the 50s, the United States military, especially the U.S. Department of Defense, recognized the need to have a more systematic and proactive approach to ensure the three dimensions of RAM: reliability, maintainability, and availability for critical systems and complex equipment. This led to the development of several methodologies of several techniques, including the failure modes and effect analysis, the failure modes, effects, and criticality analysis, the FMECA, fault tree analysis, and reliability block diagrams. All of these essential elements of RAM analysis. Today, in modern times, RAM analysis continues to play a crucial role in various industries, including, for example, aerospace, manufacturing, general transportation fields, and technology. Maybe it's best to understand RAM analysis with an example, with a metaphor. Imagine that RAM analysis is a set of tools to help you evaluate systems and their components. We have three sets of tools at our disposal: the reliability, the availability, and the maintainability. RAM analysis is a process that combines the study of these three dimensions. Importantly, these dimensions have to be examined together in order to derive valuable and practical insights, at least in RAM framework. Following the relevance of RAM analysis comes the fundamental concepts of RAM analysis. And one such fundamental concept is the one of functionability. It's a very easy word to say, but this is a crucial property of engineering systems, and it was defined by Knežević in one of his books, where he talks about the ability of the system to remain functional over time. According to Knežević, and from a functionability perspective, a system can be in one of two states at any time: the state of functioning, which he called SOFU, indicating that the system is functional, and the state of failure, indicating that the system is not working properly. Knežević was an excellent writer and researcher, but he was also a visual person, and he wanted to give a look to the concept of functionability. So he proposed the functionability profile, where he shows the system's evolution through the state of functioning and the state of failure over time. RAM analysis is closely related to this idea of functionability profile, as it requires an understanding of the functionability to perform the analysis of RAM effectively. We show here the functionability profile of an hypothetical system that is repairable, or as we may call it, maintainable. It is maintainable because after a state of functioning, when a failure happens, the system can be put into a state of failure where it is repaired and put back into operation, into another state of functioning. We also have the case of non-repairable systems. Non-repairable systems have a single state of functioning because once the failure occurs, they cannot enter a state of failure. They are either totally discarded or replaced by a new system. Examples of non-repairable systems are light bulbs or rockets. A system's behavior can be seen like a person's emotions. When we are in a happy state of functioning, we work efficiently, we contribute to the operation's success. But when we are sad, in a state of failure, we are unable to function, causing disruptions and added costs. We complete this section with the concepts of uptime and downtime. Uptime is the time during which a system, such as for instance an aircraft, is functioning or it is able to function. On the other hand, downtime is the opposite time. It refers to the period of time during which the system is unavailable to perform its desired function, so it's in a state of failure. To calculate uptime, we need to add the times in which the system is in a state of functioning. Conversely, to calculate the downtime, we need to add the times in which the system is in a state of failure. In this section, we have explored the meaning of the functionability profile. Moving forward, we will delve into the three dimensions of RAM, beginning with the topic of availability. Availability is used to assess the performance of repairable or maintainable systems, and it's not used for non-repairables. And this follows from the fact that availability accounts for both reliability and maintainability properties. The goal here is to summarize the functionability profile of a repairable system. There are many ways to capture and measure the concept of availability. We will see 4 of them. But let us look first at the formal definition of availability. Availability can be defined as the ability of a system to be in a state where it can perform its required function in a certain environment, or in other words, under given conditions, at a given instant of time or over a given time interval. As you can see from the definition of availability, the classification of availability is flexible, it varies according to the downtimes, to the definition of the downtimes, and the time span to which it refers. So, for example, you can define availability for a given time instance, that's a type of availability, or you can define it for a given time interval, that's another type of availability. There are many possible metrics for availability, including operational availability, instantaneous availability, average uptime availability, and steady-state availability. To understand their calculation and implications is very important for choosing which of which to integrate in your analysis. Operational availability is a measure of the real average availability of a system over a period of time. We designate it real because this is the availability that we actually experience. For example, for an aircraft, this is the percentage of time the system was operating or was available to operate. It is calculated based on actual events that have happened to the system. The operational availability is the uptime over the uptime plus the downtime. And because there is a relationship between the state of functioning and the uptime and the state of failure and the downtime, we can transform this equation into the following. Operational availability can be considered to be conceptually simple. It is the portion of time that the system is operating or ready to operate. Calculating it based on past data is more or less straightforward. However, estimating availability by resorting to probability theory is much more complicated, as we will see. In order to define instantaneous availability, we need to define a function. This function is called the status function, x of t. X of t equals to 1 when the system is functioning, so we are in a state of functioning, and it is defined as 0 when we are in maintenance, in a state of failure. This function is very important because it captures the functionability profile. The instantaneous availability at a specific time is represented by the probability that the status function at that time equals to 1, or in other words, that the functionability profile at that time is in SOFU, which can be calculated by the expected value of the status function at that time. Mean availability is different from instantaneous availability in the fact that we care about a time period instead of a time instant. In that time period, mean availability is the proportion of time that the system is available for use. To calculate it, we resort to the mean value of the instantaneous availability over the period from the beginning of life of the equipment until a specific time point. Mean availability is often more meaningful than instantaneous availability because it relates more directly to operational availability. Here, mean availability and operational availability both relate to intervals of time. Operational availability is about the precise calculation of the uptime over total time, while mean availability is a more probabilistic view of the concept. The steady-state availability of the system is the limit of the main availability that we have already talked about when time tends to infinitive. It describes the mean availability of the system when we analyze an infinite amount of operating time. I hope that as we explore the metrics and formulas, we realize the importance of availability metrics. So, let us continue the journey and discover more opportunities in the maintainability dimension. Maintainability is the ease by which a system can be restored to its functional status after a failure. This type of analysis only applies to repairable systems, so it makes no sense to talk about non-repairables and maintainability. For repairable systems, the random variable of interest is the time to repair, or the time that you spend in the state of failure, in SOFA. We often also measure the metric of mean time to repair. What is the difference between maintainability and maintenance? In essence, maintainability relates to the design stage, and its goal is to design products and systems that make maintenance more straightforward and efficient. In contrast, maintenance involves executing the actual tasks to ensure the system's ongoing performance. Let me give you an example of the difference between maintainability and maintenance. Prior to maintainability analysis, the positioning of components in a car engine was not optimized. For example, crucial elements like the oil and the air filters were below the engine, making it necessary to remove the entire engine when replacing these filters. Maintainability involves several probabilistic parameters, as in the case of availability. However, we will skip the mathematical details. Let us now see the dimension of reliability. Reliability refers to the ability of a system to operate without failure. Focus is in evaluating if the system is failure-free without considering the maintenance time. A formal definition is that it is a measure of a system's ability to deliver an intended function over a specified time measured in calendar or usage time. An operational metric of reliability is the mean time between failures. The mean time between failures represents the average time or expected duration between two consecutive failures of a system. It is a critical parameter used to assess the reliability of a system, indicating how long it is expected to operate without experiencing a failure. For simplicity, we will not cover all the equations and metrics utilized to estimate reliability. Instead, we will focus on studying the tools used in the field of reliability. We will start by the failure mode's effects analysis. In the late 40s, the US military shifted to prevent failures rather than just fixing them. FMEA, failure mode and effect analysis, a qualitative failure analysis method, was then used to link potential failure, mission impact or effects, and causes or failure mechanisms. Given its significance and effectiveness, this technique is still in use today. Since the focus is on failures, this method is essentially an approach to observe the system's reliability. FMEA and FMECA are two closely related tools. Both tools try to identify failure modes that can potentially cause a failure. However, FMEA is qualitative. It explores what-if scenarios, where FMECA includes more quantitative calculations and computations, especially of criticality. FMECA helps us prioritize and optimize maintenance actions to ensure performance by analyzing the dimension of criticality, which combines severity and probability of occurrence. Let us consider an example of a failure mode in an aircraft's hydraulic system. The failure mode is hydraulic fluid leakage, and it can derive a series of effects, such as the loss of hydraulic pressure, reduced control of aircraft systems, and potential loss of critical functions. The mechanisms, the causes of this failure mode are 5, such as damage or worn hydraulic seals, loose or improperly installed hydraulic fittings, and others. We have talked about this, but an interesting aspect of FMECA, FMEA does not include this, is the criticality calculation. Criticality is used to identify system priorities and to classify risk. There are two common criticality methods that FMECA uses: the failure mode criticality number and the risk matrix. In FMECA, criticality can be calculated by the failure mode criticality number. This number provides a value to measure the risk of a failure mode. So for each failure mode, you calculate the failure mode criticality number. Importantly, the criticality number for the failure mode is the C of M, the conditional probability of loss of function or failure effect probability is the beta, and the failure mode ratio is the alpha. The probability of failure, which we also call failure function, is given as f of t. To differentiate between the alpha and the beta, remember that the alpha represents the failure mode ratio, indicating how often an item will fail in a specific manner. On the other hand, beta is the conditional probability of a failure effect happening when a particular mode occurs. Beta is often set to 1 to consider only an end effect resulting from a failure mode. FMECA can also use a more qualitative approach instead of the criticality number calculations. So we can use a matrix tool instead of equations. And the risk matrix for FMECA is kind of like a visual tool that allows us to assess the risk level of different failure modes based on their severity and probability of occurrence. It is a grid with severity levels on one side and occurrence levels on the other side, and each failure mode is assigned a risk score based on the intersection of the severity and the probability of occurrence in the matrix. A reliability block diagram is an alternative analysis of the reliability of a system. It looks at the system and divides it into components and their relationships. So it gives a visual explanation to evaluate the effects of each component on the reliability of the total system. Let us look at a metaphor to further understand what is a reliability block diagram. A reliability block diagram is like a map that shows you the roads, the paths within a complex system. In this map, we connect all the system components with lines. We have already talked about the failure function, but a related concept is the reliability function, and this is a fundamental concept in reliability engineering. It represents the probability that the system or component will operate successfully until a specific time, given that it has already survived up to that time. In these calculations, the duration of maintenance events are not considered in the calculations. Reliability block diagram analysis is much centered on the concept of reliability function, and it consists of reducing the system to simple series and parallel blocks, which then can be analyzed using appropriate reliability formulas. In a series system with n components, the overall reliability is calculated by multiplying the reliabilities of each individual component. That is, because all components in a series must function successfully for the entire system to work. If one subsystem, one component doesn't work, the system doesn't work also. We can only do these calculations because we assume that the components are independent. Independent components refer to elements or parts within a system that do not affect each other's performance. In other words, their behavior is independent, and failure does not influence the operation or failure of other components within the system. In order to calculate the overall reliability of a system in parallel, we use the complement of the probability that all components fail simultaneously. Let us now talk about fault tree analysis, and let's begin by the difference between fault tree analysis and the methodologies of FMEA and FMECA. FMEA and FMECA, as discussed, are used for finding all possible failure modes. They look at failures of components and look for their effects for the system. So it's a bottom-up approach. They are efficient, but they have the drawback that they try to discover all sources of failure, even if only a few of them have severe consequences. Also, they are rather qualitative, as we have previously discussed, even when criticality calculations are made. In contrast to the bottom-up approach of the methodologies of FMEA and FMECA, we have the fault tree analysis, the FTA. This is a deductive method that goes top-down. It begins at the top event, for example, loss of drone control, and searches for all the possible causes at the first level, for example, critical failure, perturbation, or collision. Then the reasons for these causes are investigated in a third level, until the basic events. The fault tree is complete if all these events are depicted, showing how the lower events, the basic events, causes the top event. Importantly, a fault tree can be converted into a reliability block diagram. When converting the fault tree to a reliability block diagram, the logic gates are transformed into reliability block diagram connections to represent the relationships between the events. So an AND connection becomes a parallel connection. In the fault tree, a parallel connection is represented by the logical gate AND. The upper event will occur if and only if all the lower events occur. Similarly, an OR connection becomes a series connection. In a fault tree analysis, a series connection is represented by the logical gate OR. The upper event will occur if any of the lower events occur. In conclusion, through methods like FMEA, FMECA, fault tree analysis and reliability block diagrams, engineers can do many things, like identify potential failure modes, assess their effects or impact, and develop strategies. So now let us look at the strategies of maintenance and discover how they connect with RAM analysis. The strategies of maintenance play an important role in the broader context of RAM analysis, as they are directly connected to improving systems reliability, availability, and maintainability. In general terms, there is no consensus on the maintenance strategies. However, we adopt the terminology of Meissner from 2021, which is relatively well known and well accepted. In particular, we consider 4 types of maintenance: corrective, preventive, predictive, and prescriptive. Corrective or reactive strategy may sound like a no-strategy, but it is a real approach. In corrective, we wait for things to fail before doing a maintenance action. This type of strategy should only apply to non-costly, easy-to-replace, hard-to-inspect components with low criticality. Examples are a light bulb or a coffee machine. Preventive maintenance is a strategy that involves setting up a fixed schedule of inspections and tasks. This strategy aligns perfectly with the saying, "An ounce of prevention is worth a pound of cure." The definition of the schedule intervals depends, of course, on the availability of data on failures. Predictive or condition-based maintenance is more proactive. Instead of relying on fixed schedules, it involves continuously monitoring assets to detect deviations from normal condition. The convergence of artificial intelligence, machine learning, and in-depth knowledge of physics is vital in advancing the effectiveness of this strategy. Prescriptive maintenance takes us to the next level. It predicts when maintenance is required, but also provides insights into the reasons for the decisions and incorporates scheduling in the estimation process. This advanced strategy combines the best of predictive analytics and optimization. Choosing the right maintenance strategy involves understanding the options available. Corrective is suitable for certain non-critical assets. Preventive maintenance offers planned inspections and tasks. Predictive and prescriptive rely on sensors and software to detect anomalies and forecast failures. There is no one-size-fits-all strategy. It is about finding the best combination for your assets and adjusting as you gather data and experience. With the help of RAM and utilizing several strategies and tools, airlines are better able to perform as expected. From corrective to prescriptive, they choose their strategy. But how to understand and estimate reliability in concrete terms? Let us learn this in the next lecture. Until then, see you and have a good flight.